A propositional variable is a symbol, usually a single lowercase letter such as P, Q, R, that stands for a simple statement which can be either true or false but not both. Think of each variable as a light switch. It is either on, true, or off, false. Connectives are the logical glue that let us combine variables into more complex statements. The basic connectives are: negation not flips the truth value, like turning a light switch to the opposite position. Conjunction and is true only when both parts are true, like saying the road is wet and it is cold. Disjunction or is true when at least one part is true, like you will bring an umbrella or a raincoat. Implication if then is true except when the antecedent is true and the consequent is false. Biconditional if and only if is true when both sides have the same truth value. A well-formed formula, WFF, is any expression built from variables and connectives according to the syntax rules. A variable alone is a WFF. If phi and psi are WFFs, then not phi, phi and psi, phi or psi, phi implies psi, and phi if and only if psi are also WFFs. For example, with P equals it rains and Q equals I carry an umbrella, the expression P and Q implies not P is a WFF, because it follows the construction rules step by step. To build a truth table for any propositional formula, follow these steady steps, much like filling out a spreadsheet. List all distinct variables appearing in the formula, for example P, Q, R, count them. Let n be the number. Create 2 to the n rows. Each row corresponds to one possible combination of truth values for the variables. Start with all false at the bottom and count up in binary order, changing the rightmost column each row, the next column every 2 rows, and so on. Write the formula's structure across the top, adding a separate column for each subformula you will need to evaluate. For example, P, Q not P, P and Q implies R. Fill the columns from left to right or from the simplest subformulas to the most complex. Use the truth definition of each connective. Not phi is true when phi is false and vice versa. Phi and psi is true only when both phi and psi are true. Phi or psi is true when at least one is true. Phi implies psi is false only when phi is true and psi is false, otherwise it is true. Phi if and only if psi is true when phi and psi match, both true or both false. Read the final column. It gives the truth value of the whole formula for each possible assignment. The method works for any size formula. The only practical limitation is the exponential growth of rows, but for exam problems n is usually less than or equal to 4. Explanation: once the truth table is complete, you can answer what is the overall truth value of the compound proposition under each circumstance by simply looking at the last column. For instance, consider the formula P or Q and not R. After constructing the table with variables P, Q, R, you will have 8 rows. The last column shows true in exactly those rows where either P or Q or both are true and R is false. If you need the truth value for a particular real-world scenario, say P equals the alarm sounds, Q equals the fire department, is called R equals the building is evacuated, plug the corresponding true or false values into the row, and read the result. This systematic approach removes guesswork and ensures you treat every possible case. A formula's classification follows directly from its truth table column. Tautology: every entry in the final column is T. The statement is unconditionally true, like the law of excluded middle P or not P. No matter what the world looks like, the formula holds. Contradiction: every entry is F. The statement can never be true. An example is P and not P, which is like saying the light is both on and off at the same time, impossible. Contingency: the column contains a mix of T and F. The truth depends on the particular assignment, such as P or Q. It's true when at least one of P or Q is true, false only when both are false. To classify, simply scan the final column after you have the table. No extra algebra needed. 2 formulas are logically equivalent when they have identical truth values for every possible assignment of their variables. To verify this with a truth table, list all variables that appear in either formula. Create columns for each subformula of the first expression and each subformula of the second expression. Fill the table following the step-by-step method. Compare the 2 final columns. If they match row by row, the formulas are equivalent. For example, to prove De Morgan's law not P and Q is equivalent to not P or not Q, build a table with columns for P, Q, P and Q, not P and Q, not P, not Q, and not P or not Q. The last two columns will be identical, confirming the law. By repeating this process, you can derive many standard equivalence laws such as identity, domination, absorption, distributive, and so on, and store them as shortcuts for future reasoning. A fundamental tautology is a formula that is always true, and its truth can be shown by a tiny truth table. Two classic examples. Law of excluded middle, P or not P. P true, not P false, result true. P false, not P true, result true. Every row gives true, so the law holds for any proposition. Double negation, not P if and only if P. P true, not P false, not P true, equivalence true. P false, not P true, not P false, equivalence true. Again, the final column is always true, proving the equivalence. These simple tables act like proof certificates. They leave no room for doubt because they examine every possible world. The same technique works for any candidate tautology. If even a single row yields false, the statement is not a tautology. Explanation: when a complex formula contains a subexpression that is itself a tautology or a contradiction, you can replace that part with the constant truth values T, always true, or F, always false, greatly simplifying the whole statement. For instance, consider P and Q or not Q implies R. The subformula Q or not Q is a tautology, always true. Replace it. P and true implies R simplifies to P implies R because P and true is just P. Similarly, if you see P or Q and not Q, the term Q and not Q is a contradiction, always false, so the expression reduces to P or false, which is simply P. Recognizing these patterns saves time on exams and prevents you from building unnecessarily large truth tables. Typical exam tasks and quick ways to handle them. Prove or disprove a tautology – build the truth table for the whole formula. If every final entry is true, you have proved it. If you find even one false, you have disproved it. Find a counterexample – the row where the formula evaluates to false gives a concrete assignment of truth values that makes the statement false. Stated in words example, take P equals true, Q equals false. Derive the contrapositive – for an implication P implies Q. The contrapositive is not Q implies not P. Show they are equivalent by constructing a two-column table for both. The columns will match, confirming the rule. Show equivalence of two formulas – as described in topic 5. Place both formulas side by side in a truth table and compare their final columns. If they match, write end of proof. Practicing these patterns builds intuition and speed. Even seasoned students stumble when making truth tables. Common traps and how to avoid them. Missing rows with n variables, there must be 2 to the n rows. Forgetting a row can change the classification. Always write the row count at the top and double check. Incorrect order of evaluation. Treat not as having highest precedence, then and then, or then implies then if and only if. Use parentheses to avoid ambiguity. Wrong implication rule. Remember that P implies Q is false only when P equals true and Q equals false. Many mistakenly treat it like and. Copy-paste errors. When copying a subformula's column into a later column, re-evaluate rather than copy blindly. A small slip propagates. Misreading T/F as 1/0. If you mix numeric and logical symbols, stay consistent. Exam tips. Write the variable list first, draw a thin grid for the rows, label each column clearly, and check the last column before concluding. A quick sanity check, for example, does a known tautology column show all true? Catches many mistakes early.